So Daniel, we are good to start here, okay?
Okay.
Yeah, so I'll start with a quick intro and then you can take over, all right?
Okay.
Cool. So, hey guys, welcome to this webinar. I can see 12 people here in the webinar. Great to see your presence. So this webinar has been hosted via our Datagiri platform. So Datagiri is a non-profit platform which we use to host events like this and to expand the data science community here in our city in India and globally as well. So we conduct a lot of events through this platform, and webinar is one of them, in which a speaker takes a machine learning concept and goes through it, explains you how it works. So today we have with us Daniele Rosa. He's from the US. So today our speaker, he'll be taking you through a 90-minute session on linear regression with regularization. Daniele is an experienced data scientist and tech enthusiast, a tech craftsman with more than 5 years of experience. He's a lead problem solver in the financial service industry and scientific research. Daniele also holds a PhD in Earth and Planetary Science from the University of California, Berkeley, and also holds a dual master's degree, one in physics and the other in environmental system mathematical modeling. So here I'm handing it over to Daniele, who will now start his session. Over to you, Daniele. All the best.
Thank you, Vijay. Hello, everybody. So good evening for you. Here it's morning in the US, and I'm located in Massachusetts, USA, on the East Coast of the United States. I am originally from Italy, but I moved to US some 10 years ago. So I'm happy to be in this event and to be able to share with you something that I've learned about linear regression. This webinar will be presenting the concept of linear regression from an intuitive viewpoint. And I know the audience can be mixed with mixed backgrounds. So the idea is to keep it intuitive. And feel free to ask questions as we go through it. And
so Dan, you can just ask if everyone can hear you and you're audible, so they can just reply via a yes or no.
Yeah, well, we'll do that. So can you guys hear me fine?
Great. Yeah, it's clear. Cool. Okay.
All good?
Yeah.
Very good. Okay. I was going to add that, as Vijay mentioned, my formal education is not in statistics or computer science or machine learning, but I've learned that on the field, and I've studied subjects which include a lot of data analysis and statistical analysis. So the transition for me to work as a data scientist was not too difficult. So let's get started. I keep an eye on the chat if you guys have questions as we go through, and see how it goes. For me, this is the first one that I do this interactive lecture. I've done lecture in person before. So linear regression. If I think about linear regression, I always wonder why do we have this name, regression? Where does it come from? It was always some puzzling thing to me. So I think it was worth it to dig it up and find where it comes from. So in fact, we can trace that term back to the 1886 from this scientist called Galton, which studied the properties of the height of the people, the height of the parents and the height of the children. He introduced the term deviates, explaining that or referring to how the height of a person, of an individual, would deviate from the height of the group of individuals. We call now variations what he called deviates. Or I can call them deviations as well. But we don't use the term that he used anymore. We call them variations or differences. What you see here on the right is essentially a variation plot where you have the deviates of height for the height of the parents. And you see that the height of the parents is this represented by this line here. You see the deviation from the mean, which is represented by this horizontal line, is up to these values here. So it gets to +4, +3, +2, +1 inches, as well as all the way to -4 inches. When he looked at the population, at the height of the population of the children of these parents, he noticed something that it deviates would be smaller. In fact, it would go up to +3 as opposed to being up to +4 inches, or to -2.5 and so on. So that's why he introduced the term regression. Regression means going back to the mean, which is represented here by the horizontal line. So he basically, in this study, he essentially studied the variations, and he noticed that the variation from the population of the parents, the population of the children, turns out to be smaller than the variation population of the parents. And he called that regression to the mean. So let's move to the next one, which I think it's another important finding that he showed. So this is another table from his original study. On the X, here we have the height of the children. And on the Y, we have the height of the parents. Whereas here in this table, we have the counts. How many would fall into a particular XY cell, let's say. So if you look at the counts, you see that more often you have the data he was looking at concentrated in this region, so around the mean values. And then it would kind of, you would have some points here and here. This is very, very similar to what we see today when we represent our data sets in this manner. Where you might have an X variable on this horizontal axis, Y variable on this vertical axis, and then you would see your data set being kind of distributed that way. Are you guys all with me so far? How are things going? I see one yes. Anything that is very unfamiliar so far, or are you all good? Very good. Okay. I got a couple of yeses. Sounds good. So let's continue. So far, we haven't seen anything that is what we call linear regression today. But we saw a concept of deviates and a concept of correlation, a concept of variations. So let's move to the next slide. So that was, let's remember, that was from the 1886. Now, follow-up work from Lagrange and Gauss in the 1805 and 1809 actually continue, and also from Yule and other. They refer to this original work by Galton. They say, the term regression was introduced by Mr. Galton. He was dealing with the correlation of the heights of sons with their father's heights. In this case, it is found that the mean height of the sons of the parents of a given type is nearer to the mean height of the general population than the parents' height is. That is, say, there is a stepping back or regression of the sons towards the population mean. So here again, the concept of regression. And that's where we basically have the word regression getting stuck in this study of correlation. But the key part here is that subsequently, a method called the Rsquare was introduced as a complement to study variation. And it was introduced by Lagrange and Gauss during the study of celestial motion. So we have regression and least square. And now is the term, why do we call it linear regression? So here's a question. If you have a data set, like a few data sets, can you tell which one might be explained with the relationship between the two variables, so therefore the x and the y? That is a line type of relationship. Which plot on the right might be explained or could be explained by a line type of relationship? I have the answer here for you. Yeah, let's go to the chat. C and B. So I get a C, and a C and B. You know, Jatinder, I actually, when I look at B, I could see that some part of it could be explained by a line. Maybe not all of it, right? But even if you look at this part, could be explained by a line. I think you bring up a good point that maybe not all data set can be explained by a line, but maybe part of it could be explained by a line. But definitely C looks a line all the way from all the values that we see. You know, we can intuitively say, okay, this can be explained by a line. Definitely not A, or you can claim maybe in the beginning or maybe in this part here, but if you look at all of the points, definitely not A and definitely not D. Okay. So let's move to the next slide. In fact, so linear comes essentially from using a line type of relationship to explain these data sets. Now I ask you another mental exercise. Try to subtract in your head from the plot that we saw here in this slide here. Try to subtract the best line you can possibly find describing these data sets. Subtract that from the y value, and what are you left with? Can you project in your head what you're left with? Or make an estimate of what the, let's say, the deviates would look like? So I'll let you a few seconds to think about that. Especially for C, for D. Okay, here we go. So if I subtract actually mathematically a line type of relationship from the points in the previous plots C and D, this is what I'm left with. Here in C, we kind of see irregular type of noise or deviates around the 0. 0 is essentially if you ended up perfectly on your imaginary line, whereas anything else would be above the line or below the line. Whereas if you do the same for D, look what you have here, this shape here, kind of an I would say a sort of an S shape, something like that. Clearly, this point, they're going to deviate a lot from your imaginary line, and this point are going to be deviate a lot from this imaginary line. Some pattern, for sure, some pattern. Yeah, definitely in plot D, there is some pattern. If you go back, you can think about plot A will have a pattern, and the deviates will be smaller, and then smaller for small x's, smaller for large x's, and larger for middle values of x's. In fact, here, so first of all, how do we call these deviates properly? We call them residuals. So what's left, you know, a residue, what's left after you've done your mental model or your mathematical model. What's left to be explained also is referred to. And when you can do, you will see, basically, you can do a linear regression type of approach. You can use a line to describe a relationship between two variables when the residuals are defined homoscedastic. That if you just look at the meaning of this word, essentially means that they have the same dispersal, the same variations. They are dispersed uniformly after you apply your model. So these ones, they are not. They have some pattern, like you guys noticed. So we'll get to, so getting there, we'll get to the R-square actually. We'll get to the R-square. When we'll do some coding, we'll get to the R-square, not in this intro. But the term R-square is a description of the residual, but it is just one number. It doesn't show a pattern. So here we have another question from Prasad. The error is uniformly distributed. Not necessarily uniformly. It can be normally distributed, but it has no pattern, essentially. Any more question on this? Okay. Another thing that we will not look at, but it's worth mentioning, is that we can apply this model when the variables themselves, they're not autocorrelated. Autocorrelated means that the value of a variable depends on its own variable sample, maybe a time before. I think it's important to mention this, but we will not explore that. It's beyond the scope. Okay, so we saw why we call it regression. We saw why we call it linear. The goal is to fit a line. We saw the concept of residuals, which is what is left after we applied our line type of model. And let's go a little bit more in detail about what the mathematics is and what the variables are like. So essentially, linear regression is when you have two lists of variables. We often call them X and Y. Let's say X would be this list of values here, and your Y would be this list of values. And you say, okay, there might be some sort of linear relationship we would like to find. And the linear relationship would be in this form. Your Y is equal to a value multiplier A times your X plus a constant value. So if A is 2 and B is 1, you'd expect Y to be 2 times 3 if X is 3 plus 1 equals 7. And so X, we call it usually the explanatory variable from to explain, and expresses the idea that you hope that your X would be able to explain your Y, to determine the value of your Y. Whereas Y is usually called the response variable, from to respond, to be determined by X. So this is the key point. So we are looking for a relationship that is a line type. I assume you all are familiar with a line type of relationship. Your Y is determined by AX plus B. And we'll see that a little bit more in the coding part. And let's go here now. And it's worth mentioning that what we saw, simple relationship that is of a line type, can be extended, and can be extended in many ways. For instance, we have multiple linear regression, where you have more than one explanatory variable. You have a general linear model, which you have a multivariate regression model for more than one response variable and more than one explanatory variable. You have a type of polynomial regression, where your explanatory variable, so your x, is raised at different powers greater than 1. Or you have, oh, sorry about that. Or you have logistic and multinomial regression, where your response could be binary or having multiple classes. So it could be either a yes or no, or belonging to high, low, and mid values, or having multiple classes. And then you can have what they call the generalized linear model, which is a model that essentially allows transformation to the variable that you used in your regression type. This is all beyond what we want to say today. It's worth mentioning that what we see is just the tip of the iceberg, and there's a lot more that you can do with regression type of approaches. But let's look at what it means in multiple linear regression, because we'll touch on that during the coding part. So the multiple linear regression is when we said it's when you have more than one explanatory variable. And here how I represented it. So you have, instead of just x, you have x1. So list number 1 was a list of values. You have x2, the list number 2. And then let's assume you have n lists. And here represented by x1, 2, up to xn. And then you have a response variable. I will still call it y. So what we are after, we hope we can explain our y, in this case, our response variable, in this fashion, essentially. Y is being dependent of your x's, where you're gonna, instead of just having a times x, you have, in this case, it's customary to call them w, weights, weight 1 times x1, weight 2 times x2, and so on, weight 1 times xn, plus b, a constant value called the intercept. I want to make sure that, before moving on, I want to make sure that this is clear to everybody. Is there any confusion about the concept of multiple linear regression? All clear? All clear? Yeah. Very good. Okay. Yes, good to go. Very good. All right. So, all yeses. So I'm assuming that you guys know just more than the average person about regression and about stats, because you probably are passionate about it and being just in this seminar. So I assume you are already knowledgeable to a point about that. So what are the common applications of linear regression? This is taken from Wikipedia. You know, you can have, it's really widely used. It's the first thing you do when you look at the data, especially in life sciences, and they just go look for linear regression. It's just the simplest type of approach you can look at, you know, beyond just looking at the mean value of a data set. I think you skipped on a slide. Which slide did I skip? Let's see. So Lorado said that I might have skipped slide 10. Oh, thank you. Yes, very good. Thank you. Thank you, Lorado. So let's go to slide 10. So here's the thing. When you look at regression and you have many explanatory variables, you might find that there's a problem with collinearity. So what does it mean? It means that your explanatory variables, two of them could be correlated one to another, could be themselves depending on one another. You could potentially explain one of the two variables, calling one of them a response and the other one the explanatory variables. So you try to explain why having many x's, but some of your x's, they are close to each other. They behave like, they're closely behave. That's a problem that actually we'll touch upon during the coding part. Collinearity, this is something that you always need to be aware of. And here is the example that I came up with. Think that you have a model for a garden where the produce yield, so the amount of yield that you can make, is your response. So you're trying to come up with a model for how much produce you can make. And you have as explanatory variable sunlight, rainfall, irrigation, and the work amount that you put in your garden. I'm claiming that immediately you can think that there is some sort of correlation among them. So actually, let me ask you, what kind of correlation does come up to mind to you between these explanatory variables? So the explanatory variables would be these ones. Any guesses why they might be correlated to each other? Positive correlated from, it doesn't have to be positive correlated. They can just be correlated in the sense that one moves, the other one moves as well. One can go up and the other one can go up, or one can go down, up and the other one can go down, but they're always tied together. That's the problem of collinearity. They move together. So Prasad said rainfall and irrigation. I can see that easily, you know. You're not gonna irrigate if there's rainfall. So in this case, what do you think, Prasad? It's gonna be a positive or negative correlation? Opposite. Okay, negative correlation. The more it rains, the less you irrigate. And then I have another comment from Lorado. When there is no sunlight, there may be rainfall. Exactly. Yes, exactly. So maybe you start from, let's say, oh, let me put in my model all of them, but then you start thinking, oh, there's some correlation among them, so I have to do some careful consideration of that. Okay, I think you guys are getting the point very well. So keep in mind that what's really driving your explanatory variables and how they play into determining your response variable. So when that happens, what you tend to do is regularization or feature reduction. So feature reduction is another thing that we will not see, but I think I want to mention it here. So feature reduction is essentially a synonymous of explanatory variable reduction. Well, if there are multiple response variables and they are correlated, in this case, we're not looking at multiple responses, but you can see, okay, in addition to produce yield, I want to determine something else, right? I want to determine I don't know, the produce yield of a particular plant that I care a lot about, you know, carrots, or if, or the summation of two of them, or the price. If you plan to sell the products of your garden to the market, you know, another response of your sunlight, rainfall, and work amount and irrigation would be the profit that you make in the market if you sell it. And they themselves could be, the two responses could be also correlated to each other. Yeah. But again, here it goes beyond what we want to do. We want to keep it simple to having one response and allowing for multiple explanatory variables. But it's a good point that you brought up. So let me mention the effect of feature reduction. And in this case, in this context, we call it explanatory variable reduction. Essentially, what you're doing is like, you're trying to say, okay, maybe I don't need all of them. Maybe I just need, instead of taking rainfall and irrigation, I can just take irrigation. Or I can just take rainfall. You know that they are tied together. So you're trying to reduce the complexity of your model in this case. And that's feature reduction or explanatory variable reduction. Whereas regularization, that might include feature reduction, we'll see that later, is actually a way to constrain the values of your weights to kind of, yeah, I would say that the mathematical term would be constrained to calculate them, but in a constrained fashion. And let's go back here. And what I'm referring to is these weights here. Okay, thank you again for keeping me on track and not skipping the slide. Let's go to the common application. Common application of linear regression. So many, as I was saying before. It's the first thing you do, the first statistical analysis, the first model you go to, and you can see example of trend lines, where let's say you want to understand if the gross domestic product, the oil prices, or stock prices, they have been moving regularly up or down according to a line over a period of time. And epidemiology, and here is an example from Wikipedia. Early evidence relating to tobacco smoking mortality and morbidity came from observational study, employee regression analysis. And in this case, there was also an addition to the modeling that we talked about before. They actually added spurious correlation, so fake correlation, artifacts correlation, when analyzing the data. And typically, the reason you do that, you add them to see if they play an important role in your model, if they can come up to be important. If they do, there's something wrong with your modeling. You expect not to come up as important because you fake them. And then in finance, it's also used this regression type of approach, where you have a constant of beta, which is the beta. Actually, this beta is the reverse that we saw in our slides. Yes, but because essentially here you want to see if that particular, in finance often you see, okay, is this particular stock moving as much as the market is moving? Is it going up as much as the market is going up? And then you have application in economics. And here again, you look at if there are explanatory variable for your key economic variables like spending, inventory, purchases, imports, and demand, and labor supply. So many applications. This is going to be a very, very powerful tool. So I think at this point, I'm ready to move to look at some code to support what we just said. Any last question from you? Okay. Okay, so here we go. We're going to see in this Python notebook, we're going to see the linear regression using scikit-learn and regularization of linear regression and how it's implemented. Again, feel free to stop me here to ask questions. So here is essentially, this is a notebook which has content, so words, but it also has a lot of code. And my idea is to explain a little bit about the code, because we want to know the concept, but also we want to know how to code them. So here's a question. What if the variables are categorical? So there are techniques to account for categorical variables. But again, here we are thinking about these variables as continuous. So we're thinking about a certain amount of rainfall that varies from 0 to how many millimeters you can have. And you can pick your preferred time frequency. You can look at daily irrigation amount, or weekly or hourly. But there are techniques to account for categorical inputs. And there are techniques for dealing with that in regression, but there are also other models that you can apply. But you don't necessarily drop the variables. You try to include them if those are the variables that you think are going to drive your response, and essentially you're after your response. So in the real world, you're going to have to do whatever it takes to explain your response, because the goal is explaining the response. Either you can plan an experiment where you make new measurements that are maybe easier to deal with statistically, mathematically, or if you cannot, you try to deal with your response somehow. Okay. Yeah. Well, thank you for the question. Okay, here we go. So we said this is a coding session, so there's a lot of coding. Here what you see, essentially, I'm telling my compute system, my compute environment, to load up some libraries. Make some settings. Again, more and more library, plotting library, scikit-learn libraries. I don't think I'm going to use all of them, but I have that as part of my minimal import. Typically, you don't want to import what you don't use. In Python, it's not so bad because they're not really loaded until you use them. But here's this. So I'm importing libraries. So essentially mathematical tools, statistical tools, plotting tools that somebody's done. And here we go with the regression. So we have, here I'm mocking up a data set. A data set that consists of two variables. So we're looking at simple linear regression. Well, we said that there are two lists, and you're after some sort of relationship between the two variables, x and y. So my x is going to be a simple list 0 to 9. So here in Python, I do just give me a range 0 to 9. Here's the trick that you say 10, but it actually goes to 9 because it goes one few element, so that the actually count is this number here is actually 10. And here I'm creating my y, by adding to a line type of response, which is a x alpha plus beta. I'm adding to alpha in this case, which is my slope, or the slope of the line. I'm adding a Gaussian noise. So what it turns out to be this y here. If I were to run this again, it would produce different numbers because there's a random component to this. If I plot these numbers in a scatter plot, this is what it looks like. I look at this data and say, okay, this is going to be a line. Definitely this is going to be a line. It looks like a line. And we said x is the explanatory variable. So by looking at x, can we say something about y? Very, very intuitively here, you know, when x grows, when x gets bigger, y gets bigger. So y is really responding to x. Here there's a reference to what we call it regression, what we call it linear. We said that in the prior slide, so we don't look at that again. But here is what we are after. We think that y, call it a line. I'm just explicitly saying this is going to be a line type. Is going to be alpha x plus beta. Let me make it larger. So now I have this intuition that my y can be explained by a line type of relationship with x, and I say, okay, how do I find the line? So this is the tricky part. How do I find the line? So what I've done here, I created many lines, like 100 lines. So here I know where I start from. I know my alpha and beta originally. So what I do, I take those and I add some random noise to alpha and beta. And then I plot a lot of lines near my original alpha and beta, my slope and intercept of the line. And I plot them near the points that I created with the original alpha and beta. This is just to express the idea that when you're looking for the best line, essentially you're trying out all these lines. You're thinking, oh, maybe there could be the good one here. Maybe which one is the good one? So quiz, which one is the good one? Anybody has a guess? The line closest to points, passing close to all points. So yeah, the answer is right. Where it has the least error, the mean deviation, yeah, they're all correct. So, but we need a way to quantify that deviation. Y minus y bar. So what would y bar mean in this case? I think you would mean the average y. So let's look what it is. They are correct. They are correct. Yes, mean y. This one is actually a special line. The line that has no slope, but it has an intercept that is equal to y. So essentially, they're all correct. You want to get as close as possible to the line, to the points, But there is a way, you know, we have to define what is close to be as close to a point. Here we want to say we need a measure of being close. We need a measure of distance. So in order to find that, we have to introduce the sum of squares residuals. So we talked about residuals before, but now we are also talking about squares, and we're talking about the sum of them. Let's look what it is. So the intuition is clear. We all have that intuition, which is the right answer, but how do we quantify that precisely? In this plot here, I have, again, my points that I had before. But here, I'm adding a line. Just, this is not necessarily the best line. This is just a line. One of them, the ones that we saw before, just one of them. But I'm adding visually what deviates the difference of the points from that line, or it's better to say from the line to the point is. So you see that this particular line is good for the first point and has some difference to the other point, some distance to the other point. Just a curiosity, like a plotting curiosity here, in order, if you want to create those distances, what I do here, I basically go through all the value of y, and I say, okay, give me the, first of all, I create a line here, line of points here, and then I say, give me the min and max range for a vertical segment that I want to draw, and then add a label just for the first point because I want to know what I see on the plot, and then draw for me a vertical line that is at x value being the x that I'm considering, and has a mean and max y according to the particular realization of y values that I have. And then I'm adding labels and color and the weight. I think this is a cool tool to use when you're trying to see something in your plots. So what is the distance? In this case is the sum of square of the residual. So we saw the residual is the difference between the point and the line, but and that is expressed by this difference. But I also want to square it, and I want to sum it all for all points. What the square does guarantees that the error that you make, let's assume you make a negative error here, I'm sorry, you make a positive error here and a negative error here, you don't want the error to compensate. You want basically to take the full error here and the full error there. So basically, whatever you get, positive or negative, you make it positive by squaring it. And then you count all the points. So this is a key part. We introduce the sum of square of the residuals. That's going to be our distance. So each line, each of the lines we saw before, for each one of them, we can compute the sum of square of the residuals. The sum over all points of the difference, but square. So if you first you do the square, and then you sum it up. And somebody brought it up during our chat. Somebody brought up the mean y, or the average y, as a measure of error. In fact, that is present here. That is basically the first, the most simple line type of approach you can come up with, and that's going to be sort of your reference. So if you weren't told anything, you would say, okay, my worst case scenario is that I can think about my point as having one value, not dependent on x, just one value of y, in this case about like 20 something, 21 or something. And I'm going to say my response is on average 21. But that's kind of the very, very, very minimal approach to describing your response. And in fact, your response does not depend on X, so it's not explained by X. But if you were given a list of Y values, you would say, okay, my Y values are roughly 21. With the linear regression, we want to go beyond that. But let's see what it means. So in this case, the sum of square, we call it Y. The sum of square of the Y does not involve any X, does not involve any concept of explaining why using X. Is essentially what some of you refer to the chart. It's like the difference between the Y point and the average of the Y point, square and summed up. So if we do a good job in finding the best line, we expect that the sum of square of the residual of any line that we find is going to be less than that. We expect at least to be better than that kind of response. So if I were to draw a line here, I can draw it here, and it's going to have a smaller sum of square of the residual than the sum of square of the Y. And here is where we can introduce the R-square. This is often called the score when you do the regression approach, linear regression approach. And essentially it is comparing your sum of square of the residual for the line that you have found. Let's say you do let's say you find the good line and you say, oh, how good is that line compared to the very, very simple approach, which is just an average. You can quantify that by using this formula. So here, let's look at the formula. If your line is a good line, you expect the sum of square of the residual to be small, because you expect your line to be very close to your points. And therefore, if this is small, you're going to have 1 minus something small over something that is constant, depending on the Y values, in this case, and the points. And what you see is that the better you are in finding your line, the better you are in minimizing the sum of square of the residual, oops, sorry about that, which is this term here. And therefore, the higher your R-square is. So again, smaller sum of square of the residual and larger the R-square, the better the best line is at explaining the response variable. How are we doing with the math here? Are we all on the same page? Yes. Any question about the coding part? Any curiosity about the coding part? I've used very straightforward tools in this case. Is there any question about that? Okay. Good to go. No question. Great. Okay. Finding the best fit line. So now we're introducing another term, the fit. You will see that, you will hear that often. What is the fit? The fit is just looking at the dictionary to be suitable for someone or something. In fact, linear regression is also known as finding the best fit line. So we'll just find the best line, the one that fits the most the data that we have. Again, we said the sum of square of the residual is the measure we're after. We're trying to minimize that. And there is now there are different ways to find the minimum sum of square of the residuals given a line, or what is the line that has the minimum sum of square of the residuals. When the model is simple in the sense that it just has one explanatory variable and one response variable, mathematically can be solved. Mathematically can be solved. You can say, okay, let's assume I have this line. Let's assume I have these data points. You can calculate explicitly the sum of square of the residuals. And there's a mathematical way to find its minimum through calculus by taking the derivatives of the sum of square of the residual with respect to alpha and beta. And I don't want to show that here, but there is a mathematical way to do that. And what you end up doing is that you can determine your beta in this way. Beta is going to be your intercept in this case, which is the average y, minus alpha, the average x. And let me go to the question. I saw the question, but let me continue here. So you have your beta determined by your average values from the response and explanatory variables, and including also alpha. And then you have your alpha that also depends on your points. So everything is determined. You determine alpha first, and then you determine beta. So that's mathematical. And then there are ways that are programmatic, and we'll talk about that. Let me go back to the question. So okay, there's a question about overfitting. So this concept of overfitting is often introduced when you have overfitting is often introduced when you have many explanatory variables, or is often introduced when you have a very complex model. What we have in this case is a model that has two parameters and at least how many points do we have? 1, 2, 3, 4, 5, 6, 10 points. There's a ratio between parameters and number of points that is 5 to 1. We can still claim that this model is sufficiently simple given the number of data points. But the problem that you brought up of overfitting happens when you have many parameters trying to explain not very many data points. I can have an example here. Let's say my model were more complicated, that I was actually going through all this point in this fashion. I wouldn't explain this system with a line, but would explain this system with this response with a squiggly type of curve. Okay. In that case, I was just looking at the data and looking at the model that I came up with. If my model were to go very close to each data point, I would say this is an overfit. It's an important concept, the overfit. So let's talk about it for a sec. Once you're looking for a model, you always have to consider that the points that you are available at hand are not the full reality. That's not the full reality. There are measurements, oftentimes. The measurements have errors, oftentimes. It's not all measurements you could take, oftentimes. So it's a very, very, very narrow view of reality. So the essential thing that you want to avoid is not to describe those points exactly. So not having an overfit. So you're fitting your points with a model, but you're not overfitting. You're not trying to explain all details of those points because you know that reality is not what you're looking at. It has more that you don't have at hand. There's more measurements you can take, probably more ranges you can explore in the X and the Y, in the X and Ys. So that's essentially it. You keep your model simple. Is this a satisfactory answer for now? Did I lose you guys? Good explanation. Thanks for explaining. Okay. In depth. Okay, sounds good. So let's continue. We were at this case where we said, when things are simple, there's a mathematical formula for alpha and beta. But there's also a programmatic way to find it. So let's talk a little bit about the two things. First of all, let's look at what the sum of square of the residual looks like. So here I do another exercise. I start from the same data points, and here it's very, it's kind of faint under all these many lines. What I've done here, I've created 5,000 lines, pretty much around the best line that I know because I created a data set. But let's say this is what happens, when you're trying to go for the best line, you're trying to explore them all, potentially programmatically, or even mathematically through calculus. You're looking around the best line. You're trying to find the minimum of the sum square of the residuals. Let's see. Anything from the coding side, let's see if there's anything interesting here. Oh, here what I do, somebody doesn't like this stuff, but what I do is essentially, in order to plot this data, I start from empty list and then I append to this empty list as I'm looping through 5,000 cases, I'm adding to this list. I'm completely fine with that. Some people, they say, oh, this is not a good way of programming, but I think it's just fine. And when you have to get something done, you can just do it. The other thing that I do here, which is worth noticing, is this zipping part, which in Python is basically takes two lists and it returns to you a list of two. Okay, anything else? I think it's straightforward. So here we go. I am the initial data set, my blue points, and I tried all these lines. And what I'm plotting here is the sum of square of the residuals for all these cases. But I'm plotting two plots. One, the sum of square of the residuals as alpha changes. So I'm trying all alphas here, all slopes for these lines. And here, I have a sum of square of the residual versus beta for all intercepts. Can you tell if there's a best value for alpha and beta that minimizes the sum of square of the residuals? Can you tell? To me, it looks evident. It looks pretty obvious that there are those values. So what are your guesses? What are the numbers that are minimizing the sum of square of the residuals? I have two questions for you guys in this plot, for this plot. So somebody says, Aman says 3.8, 3.9 for alpha. That looks good to me. Maybe. And beta 4 to 5. That looks good to me as well. Maybe alpha, maybe. Yeah, it could be 3.8. It could be a little smaller. So that's good. That's a good answer. But can you tell me why also you have, for the same value of alpha, you have, let's say, for this value of alpha, you have different value of sum of square of the residuals. What's happening here? So I look at here, beta is varying, definitely. Very good, jot in there. Very good. Yeah, so you guys get the point. Perfect. let's look at the same thing, but visually on a surface. Here again, it's clear that there's some value. So this is a concave surface. You got alpha and beta and the sum square of the residual here on the z-axis. And if I were to just drop a ball on the surface, you would know that it would go to a point here in the middle. And that would be the right combination of alpha and beta that's going to give you the minimum sum square of the residual, therefore your best line. Okay, let's find the values. So I show you. Dorado is stating something. So if alpha is 3.8, okay. So alpha is 3.8 with sum square residual minimum, would the corresponding beta be 5? Because they are two different plots. So I made in two plots, but what's happening here is that I vary alpha and beta together, and I try different combinations. So in one combination, my alpha could be about 3.8, but my beta could be a different value, could be 10. So beta is not the ideal one because the ideal would be around this value of 4-ish. So here I end up being here somewhat because I am the good alpha, but I have the wrong beta. So I have the good slope. Let's say I were to draw a line right here, I would have the good slope, but my beta, my intercept would be wrong. So my line would have to be taken down to be aligning with these points. In another situation, I might have the right beta, so my line would be kind of close to the points, but instead of going through the points like this, it would just be going like that. So on the average, it would be close to the point, but it would have a different slope. So in that case, I would have a good beta, but a wrong alpha. Okay, and now I want to demonstrate that the values are the same. So here I use the formula that we introduced before, this formula here, and I just implement the formula, and I call it mathematical alpha and mathematical beta, and I calculate it. And then I use those to plot, to determine the line that I want. So my y's here are going to be x times mathematical alpha plus mathematical betas for every x, and then I plot it. And I call it the best fit line model. And I plot it, and this is what it looks like. Very close. Very close. This is the best line that I saw so far to the points that we have at hand. And if I ask the system, okay, what are those values? Tell me those values. They are about 3.7 and 3.9. So 3.7-ish and 3.9. Pretty close, exactly. Now, what is the R-square? Are we doing a good job? What do you think? Just by looking at this, are we doing a good job? I would say so. The line that we drew here is very close to our points. And here I have a mathematical calculation of my R-square, and look how good it is. You very likely, you're not gonna see values of R-square that good. This happens because it's how I created this line. And we'll see later how much more complicated and much more variable is the real data. And now I want to do the same thing by using a package. So this is a very, very, very powerful Python library that has a lot of statistical tools and machine learning tools. It's called scikit-learn. Yes, of course, linear regression. So here I'm invoking that method. I'm passing my values as x and y, and I'm asking, okay, what is my regression alpha? And essentially this model here has been fit with this data point. So I have a regression model that I fit with the data points at hand. And then I ask for the regression alpha coefficient and the intercept. And look at this, they are exactly the same. Because in the background, the model does the same thing that we did mathematically here. Yeah, we'll talk about the reshape. It's not yet. It's close to the last important floating point digit. So compare these numbers with these numbers here. I think that's essentially rounding error. And I can ask to this package here, once I fit my regression here and I create my model, I can ask for the score. And the score is going to turn out to be exactly what we calculated before, R-square. Exactly that. We've done here mathematically, and here the package returns to us the same number. So very handy. The question is, what is reshaping the array? So I have a question from Lorado. What is the logic for creating the line? No, in this case, I believe sklearn is not going to do all the lines. The lines that I drew here were for understanding the idea behind the regression. Yes. Thank you, Vijay, for reminding me about the 10 minutes left. Yes. So the fact that we drew the lines is for you to understand what happens. You know, what is the idea behind finding the best line? Because you find the best line among what? Among many lines that are possible. So that's the idea behind it. But then you can find it mathematically. Sometimes you have to find it programmatically. So we'll get to that. So let's go. The last question is, what do we have to reshape? Well, we reshape because this linear regression can actually accept more than one explanatory variables, and it wants this particular format. So we just feed the library whatever formats it wants. Here you can imagine having maybe multiple explanatory variables, you know, in this column, but another column nearby. So I think here, what do we care about looking at the surface in 2D? And then I think this also gets to the question, why have we created many lines? To see what's behind the concept. So you're trying many possibilities and you're trying to find the best one. So it's important to visualize what means find the best line. And here, another thing that I want to mention is this, that true, there are mathematical solutions for this linear regression model, or even multiple linear regression models. But sometimes you are dealing with systems that are so big that computationally, it might be worth actually crawling this space of the sum square of the residuals and trying to find programmatically what the minimum is, instead of attempting a mathematical solution that requires inverting a matrix, a very, very big matrix. So keep that in mind. Sometimes there is a computational impossibility, sometimes there is a mathematical impossibility. So there are a programmatic method called the gradient descent that, you know, it will find the minimum of this surface. Now let's look at the regularization in this last few minutes that we have. the real data set. I basically loaded a data set from scikit-learn as well. It's called diabetes. So the data set about medical features. Here we have body mass index, blood pressure, and then you have many measurements of serum in the blood, and then you have a measurement of diabetes. So if I say plot these data points in a scatter matrix, which is essentially the plots that we saw before, but for all the variables that we have at hand. Here our response variable is diabetes. And explanatory variables are body mass index, blood pressure, and all the serums here. Now let's look at diabetes and how it varies with body mass index. Well, it does look like there could be a line here. It's not as straightforward as the point that I created before, as well as for blood pressure and serum. But look at serum 3. Serum 3, there could be a line, but it's a line with negative slope. So essentially here, what you can do, you can say, okay, I could pick the best explanatory variable among the ones that I have at hand, or I could try to use them all to explain diabetes. For instance, here there's a problem of collinearity, what we mentioned before. If you look at blood pressure and serum 5, here, it looks like a cloud. Serum 5 here and blood pressure here. It looks like a cloud, but there could be a line. Let's look at here, the example that I brought up, serum 5 and serum 1. If I look at serum 5 and serum 1, this looks even a little bit more like a line. So we can say these points are collinear, they vary together. In fact, here I could explain S1 using S5. Not a bad relationship. Another way to see this problem is this. I'm running here a regression model. Again, I'm loading the regression and I'm doing a fit on my data. Don't worry for the moment about train data versus test data. It's something that, again, goes beyond here the scope of understanding regression from the basic viewpoint. But what I'm doing here, I'm training this model. And then I'm running actually twice. And if I run it twice, the important thing here is that here are my alphas, or my weights, as I mentioned before. My weights, they don't come up the same. I run it once, and I have this weight for S5. I run it twice, I have this weight for S5. It changes, as well as this one changes slightly, this one changes slightly. How is that possible that running it twice create different coefficients? Well, let's look at the coefficient. And I'm actually taking 3 minutes from the Q&A session because we had many questions as we were going along, so I'm taking like 3-4 minutes for me just to get to the end of this. When we do look at the coefficient, and remember that in this fashion here, one key thing to notice that if I want a response, let's say here I'm saying, what if I want a response of 10? I can have multiple combinations of my coefficient from serum 5 and serum 1 to get a value of 10. And here I'm just looking at 2 explanatory variables, and I'm imagining the response being 10. But you can see I can have, for S1 being 3 and S5 being 2, I can have a coefficient of minus 1,000 plus 1,500, or I can have a coefficient of minus 2 and a coefficient of 8, or a coefficient of 1, a coefficient 3.5, or 5, and no coefficient at all for S1. And the important question is, that we get to the regularization, is what is, among this combination, what is the approach that is the least complex? Shoot me some answers on the chat box. What is the least complex approach here? In the interest of time, I'm going to answer this question. So the least complex approach is the one that uses the smaller coefficient or a fewer coefficient, like some cases even like not including it, having a coefficient of 0, a weight of 0. And there are different reasons for this. One reason is that it's less complex because it is less sensitive to changes in the explanatory variables. And then it's less complex also because it uses fewer variables. So how do we translate the goal of reducing the coefficient values from large to small, or even getting rid of the coefficient? We do that by introducing a regularization term in our sum of square of the residuals. So we are familiar with this that we saw before. We have our line points, our line averages, and here we have added a term to the sum of square of the residuals. And it's called L1 or L2 norm. And essentially what it does, it makes the sum of square of the residual larger when the coefficients are large. One approach is called lasso, the one with the L1, and one approach is called ridge. Once we do that, essentially we're going to drive the model to find this coefficient that are smaller, or even getting rid of some coefficients. So here I'm going to run the same model with no regularization and with regularization. I'm going to stop in a couple of minutes. We're basically at the end here, and then we're going to have 5 extra minutes for questions. So if I look at the regression as a function of the penalty, which is this term here in this sum of square of the residuals, and I say, how does the coefficient value vary as I change my penalty? And how does the R-square varies as I change my penalty? In this case, it's the normal regression. Your coefficient is going to be the same because there is no penalty. So these are the values of your coefficient from 600 to minus 200, very large. And your R-square is about 0.48. Now let's look at the regularization called lasso. See what happens. As I increase my penalty, the value of my coefficient, they shrink. In some cases, they go to 0. Essentially here, I'm getting rid of explanatory variables. My model becomes more and more simple. I have a sweet point where my penalty introduces the minimum error and the maximum score. If I do the regularization called ridge, as well as the lasso, I have shrinking of my coefficient, but I don't lose the coefficient. They are still there. They just shrink in value. As similar to the lasso, I have a sweet spot of penalty for my error, minimum error, and the maximum R-square. So essentially, by regularizing, by increasing the penalty for higher coefficient, I reduce the complexity of the model. In some cases, with the lasso approach, I get rid of features. Here, serum body mass index is completely disappear when I have a penalty of about 0.3, 0.4. S3 disappears when I have a penalty of 1. Here, I have basically essentially 3 features left. So much smaller complexity. I think I'm going to stop here. And I just want to say there's much more you can do in determining if this regularization is solid for your data set. So this is just for lecture purposes. But there's much more that you should be doing to understand if your analysis is solid. Another thing that I want to mention is that we haven't talked about regularization. And I'm sorry, we haven't talked about cross-validation, which is an important technique to use, and it goes beyond the scope for this tutorial. I have a question from Lorado, 2 questions. How does the lasso, here we are officially in Q&A, how does Lasso get rid of features? And why the same thing does not happen in Reg? So Lasso gets rid of feature, and this is not easy to grasp if you don't draw it, but essentially the fact that you have a module here instead of a square, what it does, it creates a particular shape of the space. If you look back here, this is your error space. And this space essentially is such that when alpha is 0 in some cases, and you have many weights, alpha will be your weights. When alpha is 0, that's a minimum spot. So basically it snaps to the axis of your hyperplane. And in some cases, you just lose some coefficients. Again, it would require a little bit of, drawing and showing some graphs of the sum of square of the residual, but essentially the point is that the surface of the sum of square of the residuals becomes such that you are drawn to having coefficients being 0. It becomes a sort of a diamond type of shape, and you are snapping to some axis. Yeah, I found, so Satya, I'm responding to you about some good resources. Well, GreyAtom will have specific in-depth courses about that, I'm sure of it. And one thing that I go to is the scikit-learn library itself. If you look at the scikit-learn library and you look for the regularization, the ridge or lasso regression approaches, you will find references there, you'll find examples there. It's a good source too. So for R will have similar libraries. R will have these basic regularization approaches as well as scikit-learn. R will have that too, no worries about it. In fact, I have colleagues that they use R and then it's all fine, it's all similar. I find Python more like a programming language and R very useful for very quick looking at the data, but less useful for manipulating data, for preparing your data for the model.
Thanks, Dan. Guys, any more questions? Because I think now we are at the business end. Okay, cool. Thanks, guys. Thanks, Daniel.
Thank you.
So it was a great audience. I really liked your participation and your enthusiasm to clear your doubts and queries. I hope this was fruitful. This was a fruitful session to you. And so this makes our efforts, the speaker's efforts and our efforts very fruitful, that you guys learned something new.
Yeah,
so,
I hope so. I hope it was beneficial to you guys that follow.
Thank you, guys. And please fill the feedback form that I've shared with you. So we also know that how you felt about the session, what can be improved, in the coming sessions. And we'll keep hosting such sessions every month, once or twice every month. So it'll be great hearing from you and, seeing you all in all the sessions that we conduct. Thanks, Daniel. So can I end the meeting now?
Yep. Thank you.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.